Thank you. Good morning. I'm going to be, well, thanks for coming to my talk. I know I have three competing talks right now, and there's also the competing sleep factor. So thank you very much for coming to my talk. I'm going to be talking to you about unrealistically attacking Tor with website fingerprinting. I'm Wang. I recently joined the Hong Kong University of Science and Technology, and this was work done when I was a PhD student with my supervisor, Ian Goldberg, at the University of Waterloo. Ian's the one over there with the hair. All right, so the most important word of this title here is the word on. Now, if I were to remove the word on, then it would be as if I had a paper that claimed I could realistically attack Tor with website fingerprinting. Now I don't. The reason why this is important is because there's no way for me to really claim I finally have a realistic attack against Tor. And this is because of the nature of website fingerprinting as a classification problem. You have a classifier, you get an output, you can't really confirm if the output is true or not. And so the best we can do here is we can really just set up a test environment where we know the ground truth, and hopefully the test environment is similar to the real environment. And that's why this is an important issue. Maybe there are differences between the test environment and the real environment that we aren't sure about, which may cause accuracy to be much lower than we thought. Now, another way to do this would be for me to really just go out and attack real Tor users, but since I'm not from a certain university, I can't do that. So let's move on. So website fingerprinting. So what is website fingerprinting? You might be asking. Website fingerprinting can be explained from this simple problem. There's this client, and this client is visiting a web page. It's a web page because there's a spider's web with a piece of paper stuck on top of it, and the client wants to load the page. So there's going to be a packet sequence. There's going to be outgoing packets for sending GET requests and data. There's going to be incoming data as well. And the question is, what if there's an attacker here? The attacker is close to the client, the attacker is local, the attacker is a passive eavesdropper, and what can the attacker really see? The simple answer to this is if you're using encryption, then the attacker can't see the clear text. If you're using proxies, then the attacker also can't see the destination. So we should be using both of those to make sure the attacker can't see much except your identity. And so, for example, if you're using Tor, then the attacker shouldn't be able to see much at all. But the more complicated answer is because of website fingerprinting, because of traffic analysis, the attacker can actually still guess where you're going because where you're going is going to affect the traffic analysis. And how do we defeat such an attacker? How do we pop this balloon? People have been suggesting one way to do so would be to improve the defenses, would be to enhance our currently known privacy-enhancing technologies, or otherwise known as PEDs, to pop this balloon. So this is why this is a balloon-themed talk. This is just for this joke. There's no other reason why. And we're stuck with the balloon-themed talk now. I hope it's someone's birthday today. So the pets will also cover up the page partially or fully in some way so that it's hard for you to identify what the page is. But those tend to be very expensive, and people don't want to just adopt them willy-nilly, because another thing people have been wondering is maybe those attacks aren't as scary as we thought. Maybe they're just kind of lame-ish. Maybe they're just not very useful in the real world, and because there are legitimate concerns about some of the differences between the testbed that we're talking about and the real scenario. So let's look at what this testbed is. This testbed involves a simple evaluation procedure. We are going to visit some web pages. We're going to record packet sequences for those web pages, and we're going to do some training and testing. Now, this sounds very simple and direct, but it turns out there's problems with every step of this procedure. What if clients do more than just visit pages, right? What if they're also, for example, watching a video in the background? When we record packet sequences, we sort of record packet sequence, we start and then we end. But how do we know when a packet sequence should really end in the real world, right? And for training and testing, there's this problem of what if the training set gets too old? How often do we need to update the training set? And it turns out that previous work, Jerez et al. Last year have shown that all of those are sufficient to make website fingerprinting attacks go to near zero accuracy. So we have to solve those problems to claim that website fingerprinting can be realistic. So we're going to divide those into three realistic problems. It's going to be noisy data, and then splitting, and then training set maintenance. And we're going to talk about those issues in this order. Now, in the paper, interesting. Now, in the paper, it's actually in the reverse order. So that's going to be the difference with the paper. And since this is a really long talk, we want to remind people which part of it we're on. So we're just going to add a little bar to the bottom left that goes like this. All right, so first of all, we're going to talk about noisy data. How do we deal with noisy data in a realistic scenario? By noisy data, I don't mean the classification noisy data, which is just incorrect labels. What I mean is noise, for example, background music that you are loading in one browser. This is baby's first browser version 0.01. You're loading it in one browser, and then you start a new tab, and then you're doing something else. You are looking at dogs now. So the question is, the music is still going on, so the data is still incoming, and you're also now browsing a web page that isn't using a transparent image. So what are you going to, what is the attacker really able to figure out that you're doing this? Can they really know that? Because now there's a lot of noise in this data. And what this shows up in the attacker's data set is the attacker is going to see some noise, they're going to have the original page, and the attacker is going to see this combined addition of those two. And the attacker has already trained on the set of pages. The attacker doesn't really know about the noise, and so there's going to be a large difference between the training set and the testing set. As it turns out, this is very much sufficient for the attacker's accuracy to be very low. And this depends on what the noise rate is, how much noise there is. We can draw a little graph here. Those are two different website fingerprinting attacks published very recently. And you can see that for both, the y-axis is the decrease in the true positive rate. So they sort of, they flatten out just because their accuracy has reached nearly zero at the end. And you can see that a noise cells, around 10 to 20, 30 noise cells per second is enough for the accuracy to start dropping really drastically for both of those attacks. So as it turns out, if you have noise, for example, like videos, like multimedia, it's going to exceed this number of cells per second, and it's going to make those accuracy values drop. So how do we deal with this? Here's an idea. Let's say the attacker sees this. The attacker is going to try to guess what the noise is and remove that from the packet sequence, and the attacker is going to guess that this is the page that they have to identify, and then they use the standard classification technique to identify this. As it turns out, the accuracy of this is nearly zero. I'm not going to show you any values because it's embarrassingly low. It's not a good idea, and the reason why is because there are two big problems with this. Noise sequences are not actually really regular. You notice that when we're trying to guess noise, all we can really do is to try to guess something regular. But noise sequences are not very regular, and they vary relatively quickly. There's a lot of variance in how the noise rate is going to work. So that's not good. And to top it off, noise can sometimes look like this. This is noise. This is the number of packets loaded per second over a period of time for loading music. Noise can look very non-standard, so trying to remove a certain number of cells per second is it's just not going to work very well. And any disturbance you make to the original sequence is going to significantly drop the accuracy. So that's not a good idea. We can't really just remove noise from noisy packet sequences. Well, here's another idea. Instead of doing that, how about instead of training on the page, on the original page set, what if we just train on the set with noise? We just train on the noisy set so that our training set and testing set are more similar to each other. Now, of course, the assumption here is the attacker can do this, as in the attacker can figure out what noise you have and therefore add it to their own training set. But if we can allow this assumption, it turns out that we can have much better accuracy. We have restored our true positive rate to somewhere between 50 to 70%, which is not too bad at all. The false positive rate is still low. If we can tolerate a false positive rate, a higher false positive rate, then the true positive rate can go higher as well. So that is how we can deal with noisy data. And this noisy data is very loud. We set the noise rate here to be equal to the page loading rate so that we can really show that we can deal with a lot of noise that's happening in the background. So that's noisy data. Let's move on to point two. Splitting. What is the splitting problem? To put it simply, the splitting problem is the following. How many web pages did the client load in this packet sequence thing? That seems like a really difficult question to answer. How can we tell that? So we're going to talk about how we can tell that. So there are really three subproblems to this problem here. There's large time gap problem, there's the zero time gap problem, and there's a negative time gap problem. This describes the time gap between the two packet sequences that we would like to split. If there's a large time gap, it's easier, and if there's a zero, and it gets harder down the track. So those all correspond to realistic activities. For large time gap, you load the page, you read it, you have some think time, and you load the next page. For zero time gap, you load it and you click while it's still loading. For a negative time gap, you load the page, but then there's a new tab while you're already loading. So that makes it very difficult to do this. And we have solutions for all of those. We're going to do some splitting, but as it turns out, for the negative time gap, the accuracy is going to be very low, so it's not clear what we can do here. So that's still going to be unsolved. So large time gap, what are we doing here? If there's a large time, it's very simple. If there's a large time gap between two packet sequences, we make a rule. If it's larger than a certain gamma, certain number, we just say we're going to split it, right? And the reason why choosing this is very important is if we choose it improperly, then we've not split properly, and so we might have two packet sequences combined together, or we might have a single packet sequence split into two places, and for both of those, classification is going to be very difficult. So we want to choose this properly. As it turns out, we can set the rule to be if there is no packets for 1 second, then we're going to do a split here. And as it turns out, this has very little negative effect on known packet sequences. It just, with known packet sequences, we just don't have a packet sequence that has that gap. And it deals with most of the issue, right? If you're reading a page for any amount of time, it's probably going to be longer than 1 second after the page is finished loading. So those are two different ways to do this, and as it turns out, the true positive rate can be very high, as in there's very little damage to the true positive rate for doing the splitting policy. So that's mostly solved. For more details, look at the paper. And so now we're going to try to deal with the zero gap issue. So what are we going to do here? For the zero gap issue, obviously we can't just split based on the time gap. We have to try to split where there is no time gap at all. And that sounds very difficult, but there are features that we can use, that we can leverage here. For example, one feature is there's a sudden decrease in packet rate at the start of a packet sequence. Another feature we can use here is that there's a large number of outgoing packets at the start of a packet sequence. So based on this, we can really distinguish between the start of a packet sequence and the middle or end of a packet sequence. And that's how we can do splitting. That's essentially another version of the splitting problem. So there's actually really two problems here. We have some collected data, we do some splitting on large time gaps, we have some packet sequences, we try to split them some more because the large time gap thing isn't going to deal with zero time gaps. So there are actually two classification problems here. Is there a zero gap? And if so, find the split. Those are both kind of difficult. For the first one, we can answer it fairly accurately. The ideal case for this table is if the true answer is we should split, then we have a 1 there for which we guess that we should split, and we have a 1 across the diagonal. That would be ideal, and we are very close to ideal in answering the question: is there a split in this packet sequence, in this pair of packet sequences, even when there's no time gap? In finding the gap, that becomes much more difficult. For the positive case, we can still find a gap. For the zero case, the accuracy becomes a bit lower, and for the negative case, that's why we don't really have a solution here. The accuracy is much, much lower. So we can maybe find a gap better than just randomly guessing, but the accuracy is going to be poor, and that's going to significantly affect the classification accuracy. But the other two parts we can solve with much higher accuracy. And there's a classifier behind this. I'm not going to go into detail. That's also in the paper. So that's part 2. Now we go on to part 3, the final part, maintaining a training set. Now, maintaining a training set is a bit of a trade-off issue, because if a training set gets very old, then it's not going to be very effective anymore. So there's really 3 problems that we want to answer here. First of all, how much time does it take to collect a training set? Second of all, how large should an effective training set be? As in, a larger training set would, of course, have more data for the classifier to leverage. And third of all, how does age affect the effectiveness of a training set? So it's a bit of a balancing problem here, and it's kind of related in a multiplicative sense. The answer to those questions is, for the first one, it takes about 15 seconds to load a single packet sequence. For the second one, a large effective training set, for our problem, is about a few thousand packet sequences, and we're going to look at how age affects the effectiveness. We really have a bit of a trade-off issue here. We can either do a small, uninformative, and fresh training set, or we can do a large, informative, but dated training set. And both of those, either one of those may have higher accuracy, but of course we want to find a sweet spot which kind of maybe has the best of both worlds. And so if we don't manage to find a sweet spot, of course our accuracy degrades significantly. So here, there's multiple graphs for this. Here is one of those graphs showing the accuracy. The y-axis is the accuracy of classification. The x-axis is the size of the training set. We can see that if we go to a few thousand elements in the size of the training set, we can already reach a pretty high accuracy. And if we're using that, then this is the age of the data set, and the y-axis is the accuracy. About 10 days old, you can see that the accuracy drops somewhat steadily when it gets to about 10 days old, but if it's only 1 or 2 days old, which is entirely possible if we have several thousand elements in our data set and we just keep updating it regularly, we can still maintain its original high accuracy value. So the accuracy doesn't drop that drastically just across 10 days old. And so what we've really said here is we can deal with this training set maintenance issue just by finding a clever balance between the size of the training set and the age of the training set. So what's the main takeaway of this talk? We've looked at all those issues with realistic website fingerprinting, and we have proposed new algorithms, new classifiers, new solutions, new ways to look at those to tackle them, to resolve those issues. So what the main takeaway here is, we can really even though there are issues, we can deal with those issues, which is to say website fingerprinting can be realistic, it can be made more realistic, and it's going to be made more realistic. And maybe it's time for us to start looking for a website fingerprinting defense to defeat those attacks once and for all. So that's the end of my talk, and thank you for listening.